Hi everyone, welcome to the fifth class of Moving Charges and Magnetism, grade 12. Okay, today we will derive an expression for the magnetic field along the axis of a circular loop using Biot-Savart law. In the previous class, we learned Biot-Savart law. What was the equation for Biot-Savart law? dB equals mu0 by 4 pi IDL sine theta by r square. We use this equation to derive the magnetic field at a point on the axis of a circular loop carrying current. See, I have drawn a circular loop. This carries a current I. See, the current direction is I, this way. Okay. You see the top part, a small elementary length, AB. AB is a small elementary length. I will find the magnetic field due to that elementary length at the point P. This point P at a distance x from the center of the circular loop. And radius of the circular loop is capital R. Radius of the circular loop is capital R. Join a line from midpoint of AB to the point P. That I give the represented by R. This is R. Okay. And you see the current direction. At the top AP, current direction is, and drawing a tangent to AB. The current is coming out. Okay. And CD current is moving into like this. Okay. And if you find the angle between this current direction and R, this is 90 degree. Okay. Current direction and R, distance R, that is 90 degree. You have to imagine the loop is in the vertical plane. Okay. So the current and R are perpendicular. Now, this element AB produces a magnetic field dB at the point dB at the point P. And you know the magnetic field direction will be perpendicular to the plane containing current and R. Okay. So this magnetic field direction is in this way. This is the direction of dB. Direction of dB. Okay. And if you extend the x direction, the dB make an angle theta with the x-axis. So what are the assumptions here? Let I be the current. You have to write the assumption first in the beginning of the derivation. I be the current through the loop. Through the circular loop. R radius. Okay. Small r, distance from the element to the point P. Point P. Okay. This dB we can resolve into two components. dB cos theta will be along x-axis. dB cos theta. You know how to resolve. And dB sin theta will be along y-axis. Okay. Now this loop is divided into very large number of elements like AB, small elements, small elements like this. So when you total, you will get the circular loop. Take the sum of all the elements, you will get the circular loop. Okay. And you consider a diametrically opposite element CD. See, through AB current comes out, CD current moves out. So CD will produce a magnetic field at the point P in opposite direction. Okay. So at the point P, this element CD, lower element CD, produce a magnetic field in opposite direction, this way. This I am taking as dB dash. But magnitude of dB and magnitude of dB dash will be the same thing because they are only current direction is different. Elements are symmetric. Okay. So this angle theta. So this dB dash also you can resolve into two components. dB dash sine theta will come along the y direction. dB dash cos theta will come along x direction. Okay. But I told you dB magnitude is same. So the vertical components dB sine theta, the sine components will cancel out. At the point P, there will be large number of dB sine thetas due to all the elements. I told you the circular loop is divided into large number of small elements. Okay, the vertical components due to all elements, vertical component of magnetic field due to all these elements will cancel out. So vertical components of magnetic field cancel out. Field cancel out. Cancel out. Okay. Vertical component of magnetic field cancel out. But the horizontal components will add up. So you know dB cos theta, dB dash cos theta, all add up. I told you many dB cos theta will be there. Here I have shown only cos component due to element AB and CD. But it will be in between that many small elements are there. So all the cos components of these elements will add up. So what will be the total magnetic field at the point P? Therefore, total magnetic field at the point P. So all these horizontal components add up. So total magnetic field B will be, you have to integrate all these components. Integral, you are integrating over the circular loop. So you put a closed loop, dB cos theta. Okay, so all add together. And you know the equation for dB, mu 0 by 4 pi I dl sine theta by r square. Here sine theta, what is that theta there? In the equation sine theta, that theta is angle between current and small r. See, what is the angle between current? You consider the top element AB. What is the angle between the direction of current R? It is 90 degree. So in this equation, that theta is 90 degree. So we can write mu 0 by 4 pi I dl sine 90 by r square. Okay. So total magnetic field will be V equals, you have to integrate this. Integral dB. What is dB? Mu 0 I dl by 4 pi r square sine 90 into this cos theta. That cos theta is different. That theta you can see in the diagram. Angle between magnetic field and the x-axis. This theta. Okay. So to avoid confusion, I make it another letter, beta. Theta, I am making it as beta here to avoid confusion. This is beta. Okay. So this whole angle you have to change by beta. Theta become beta. Beta to avoid confusion. This also beta. So this is cos beta. Cos beta. Okay. So in the final equation, this angle is beta. So we can take constant term out. Mu 0 by 4 pi. Current is constant. R square is constant. Cos beta is constant. And integral dl. So you should integrate all dl over the loop. You get a total length of the loop. Total length of the loop is circumference only. So we can write B as mu 0 by 4 pi I by r square cos beta dl is 2 pi r. 2 pi r. Integral dl is circumference of the loop. And you see the diagram, you can find out the value of cos beta also. Okay. You know, in the diagram, beta, did you see beta? And this will be what? 90 minus beta. And this will be, what about this angle? This angle, this angle. You know, this R and this dB are perpendicular. So this will be, this angle will be beta. This will be 90 minus beta. Okay. So from the triangle, you can find out, you need to find out, this is 90 minus beta, and this will be 90, and this one, this angle will be beta. Okay. Then you can find out this angle is beta. You can find out the cos beta. Cos beta will be then adjacent by hypotenuse. Adjacent is r, radius, r by small r. So cos beta can be written as, capital R by small r. So you substitute in the equation, substitute in the previous equation. Substitute here. So B is equal to mu 0 by 4 pi I into 2 pi r divided by r square into cos beta is r by small r. So what you will get, V magnetic field equals mu 0 by, you can cancel 4 pi and 2 pi. So you will get denominator 2. Denominator r square into r square will be r cube. Numerator into I into capital R square. Okay. mu 0 I r square by r cube. And if you see the diagram, you can write small r. What is small r there? Small r, if you apply Pythagoras theorem, from the figure, small r is capital R square plus x square. See the triangle? This point you name as O. So if you find the triangle O, this point you name as C. From the triangle COP, if you see COP, what is R small r? Apply Pythagoras theorem, capital R square plus x square. So you put that in the equation. Root of capital R square plus x square, applying Pythagoras theorem. V is equal to mu 0 I r square divided by 2 into r square plus x square root. R is root of r square plus x square, the whole cube. So it is 3 by 2. So this is the equation for the magnetic field at the axis of a circular current loop. Okay, if you want, we can modify this in this way: mu 0 by 4 pi multiply by 2 pi in the numerator, 2 I pi r square divided by r square plus x square, the whole raised to 3 by 2. This is the equation for the magnetic field at the axis of a circular loop carrying current. Okay. Mu 0 by 4 pi, 2 pi r square I r square plus x square, the whole raised to 3 by 2. Okay. Then, as a special case, we can find the magnetic field at the center of the loop. Special case. Magnetic field at the center of the loop. Center of circular loop. As a special case. At the center of the circular loop. So you see the diagram. If you want to find the magnetic field at the center of the loop, see, this point has to be at the center of the loop. That means you have to put x as 0. So you put x is 0 in the previous equation, then you will get the magnetic field at the center. Okay. So x is 0. At the center, x is 0. X is 0. So what will be B? Put x is 0. Mu 0 by 4 pi 2 I pi r square divided by x 0. So you get r cube. So now rearrange it. Rearrange it. What you will get? You can cancel now 4 pi, 2 pi. You will get mu 0 I r square and r cube get by 2r. So this is the magnetic field at the center of the loop, mu 0 I by 2r. Okay, so the magnetic field will be maximum at the center because denominator has decreased now. Okay, so magnetic field will be maximum at the center. And if you move away on both sides from the center of the loop, magnetic field decreases. So if you plot the variation of magnetic field with the distance from the center, the graph will be like this. Take r x along x-axis. Okay. Then magnetic field along y-axis. So at the center, magnetic field is maximum. Then on both sides, it will decrease. This is the graph. This is what? Graph showing variation of magnetic field with the distance from the center. Of the circular loop. Okay. If there are n turns for the loop, what would be the equation? For a loop of n turns, then you have to multiply the equation with the capital N. So then what will be the equation? B equals mu 0 by 4 pi 2 pi r square I divided by r square plus x square the whole raised to 3 by 2 into n if there are n terms. Okay. So this derivation is very important. It is usually 3-mark question derivation. And we can draw the magnetic field pattern due to a circular loop. See, this is the circular loop. Okay. Now, when you see, suppose current is moving in this way. So a small portion here is straight. So here field lines will be like this, like this, like this. Okay. Direction of magnetic field lines here will be anti-clockwise, like this. When you consider the other side, field lines will be again considered because a small portion of the loop can be considered as straight. So magnetic field lines will be like this. Here direction will be clockwise. And you move towards the center, the field lines radius will increase like this. At the center, it will be almost constant. Okay. So this is the magnetic field pattern due to circular loop. So all the field lines, you see the field lines at the center, field lines will be in the same direction at the center. Okay. This is a magnetic field pattern for circular loop. In the same way, you can draw the here also, lower portion also like this. Okay. So at the center, all field lines move into, right? Like this also, all field lines move into. At the center, all field lines will be in the same direction. That's all for today's class. Thank you, children, for watching. Share, subscribe, comment on the video. We'll meet in the next class. Goodbye.